So the sibling is the node immediately to the left or right. And now I have a question that people often ask me, but since you didn't ask me, I will ask you. The answer will be coming, but I'll ask you anyway. That's 17, either in this version of the tree or in the previous version of the tree. Huh? 17's a traffic cop, but there is no 17 star in the tree. How could that happen? Because in everything that I've shown you so far, the only way values get put into the non-leaf pages is if they correspond to values that appear in the leaves. How did 17 get into the tree when there ain't no 17 around?
They got deleted.
They're updated.
Remember the hand name answer approach to the slide? As opposed to blowing out, even when it's very much the correct answer, yes. It could be that 17 existed in the past but doesn't exist anymore. And there's no point in traveling up the tree and finding values that are wrong now, because it's still an effective traffic cop. Whether or not 17 is the tree, its job is to be a traffic cop and direct traffic. That's what traffic cops do. And it directs traffic fine, even though there isn't the 17 in the tree. Speaking of which, the agony of delete. There used to be a TV series called ABC's Wide World of Sports, where they talked about the joy of victory, the agony of defeat, so I got to talking about the agony of delete. It is more complicated than insert. What do you do when you delete? Well, it kind of looks similar. You start at the root and you find the thing you want to delete. And if there's nothing to delete, there's nothing to delete. But if you do find something to delete, then you delete it. And again, there are possibilities. If, when you delete it, that leaf is still half full, done, easy, simple. Still log in to get to the leaf and find the thing I'm deleting, but it's deleted, it's done, not a problem. But it's possible that it doesn't have, and I'll just use this term D, even though it's mythical, it doesn't have enough entries. It has D-1 entries. It needed to have at least D, right? Because every page is supposed to be between D and 2D entries in it. And suddenly, well, it was okay before, and it's not okay now, which means it now has D-1. One too few, okay? The first thing that you do is the same thing with the sibling that you tried before, only in the opposite direction. Could be that you've got a brother or sister on the left or right from which you can steal an entry. Well, borrow, except you might not give it back. You're cooperating. You're shuffling between the two. You're being very friendly. So, could be that you've got 2 and it's got 4, and you're both going to be okay with 3 and 3. Or whatever it is. Or you have 1 and it is 3, you'll both be okay with 2 and 2, whatever it is. So if you can take an entry from one of your siblings, you don't deal with both, but you find a sibling that has more than D. And if there's a sibling that has more than D, then if you steal 1, it'll still have D, at least. And now you'll have D because you stole an entry, okay? Sound good? But there are 2 possibilities. Could be your sibling only had D entries also. And if you steal the entry, well, you'll be okay, but your sibling won't be. It'll be down at D-1. That didn't really help the situation. You want everything to be half full. So there are 2 possibilities. Either one of your siblings has enough entries or the siblings don't. Well, if the sibling doesn't, if you've got D-1 and it's got D, guess what? You can merge together. Because if the page holds 2D, D plus D-1 is going to be less than 2D. This is why the sibling thing, which was a useful technique on insert, is critical on deletion. So if there's enough room, cool. If there's not enough room, see if you can steal with the sibling, with your sibling still being okay. You're not going to make yourself okay at the cost of your sibling. That's not fair. But if your sibling cannot contribute to you because the sibling's at D as well and would go down to D minus one, your size, D minus one, plus your sibling size, D, allows you to merge pages together and have one fewer page. Because you can have two D minus one, since the max you can fit is two D.
Question?
Yep.
So what happened to the traffic cop up there? What is it pointing to? Oh.
Thank you.
Spoilers.
Whenever you do something where you have to adjust what's going on, the traffic cops have to be adjusted too. The traffic cop pointed to you and your sibling, now it only points to one of you. If you merge with your right sibling, it points to you. If it pointed to your left sibling, then you merge into the left sibling and it only points to the left sibling. So there's one less traffic cop than there was before. Exactly right. And you know what? Now that you've merged and gotten rid of a traffic cop at the next higher level up, the next level higher up might have too few entries in it. Again, children cause problems for their parents in this particular example. Getting rid of a traffic cop at a higher level might mean you have too fewer entries at the higher level. Well, if that happens, then maybe it can merge with a sibling. Maybe it can steal from a sibling, or maybe it can merge with a sibling. Again, there are two cases, same exact logic. If it can steal from a sibling, a non-leaf page stealing from a sibling, then everything's cool. You just steal from a sibling, you steal a traffic cop from a sibling. And if that works with both of you having enough entries in it, cool, you're done. But it could be that you can't steal from a sibling because the sibling is right on the boundary too. In which case, you can again merge with that sibling and remove a traffic cop a higher level up. And that might be okay, or again, recursively, you might have the same problem going on. In fact, it could be that you end up propagating all the way up to the root level in terms of doing the merge. So let's see how this ends up going on. And it could be, by the way, that the number of levels of the tree ends up decreasing because of the merging that you're doing. So let's take a look at what happens. Suppose that we delete the entries corresponding to 22. Deleting 22 is easy. This is the nice case. Don't worry, we're not just going to stay with nice cases. Deleting the 22 is pretty darn simple because it's still more than half full. When I get rid of the 22, bang. 22 became invisible all of a sudden, not an issue. But now let's suppose that we delete 20, the entries corresponding to 20. Okay, so let's see what happens with the 20. Notice the 20 has a kindly neighborhood spider sibling, friendly neighborhood spider sibling. You delete the 20, you can steal from the 24, 27, 29 node. So there goes the 20, and there goes the 24 to the left. But notice, and it's important, the traffic cop up above, it was 2430, the 24 has to change to be the 27. Because when the 24 got moved over, the leftmost value inside the sibling became 27. So the things less than 27 are on the left, the things greater or equal to 27 are on the right. Everybody cool? And notice how the middle key again got copied up, replacing the 24 with the 27. We didn't insert a new entry, we modified the entry that was above to correspond to the new middle value. The new middle value is 27. It used to be 24. So again, this is the way it used to be. And when you steal from your sibling, well, again, it's cooperating. It's a friendly theft. The 27, right? 24, gone to the left. Now, again, you're both okay on the 19 and the 24, 27, 29. Everybody cool? Question? And, okay, that all is very nice. Now let's suppose we delete 24. So again, now what we want to be able to do is delete the 24. When we delete the 24, and again, let me show you back over here, going up. We're gonna delete the 24, and before I show you how it works, let's see what the problem is. The 24 reduces the number of things down below 2. You can't steal from either sibling because both siblings only have 2 entries. And that would fix you, but it would put your sibling in a fix. So there's nothing you can do about that in terms of stealing from a sibling. So we're gonna end up doing a merge. We're gonna do the merge of the node that now only has the 19 in it together with the 27, 29. So we're gonna see what we can do about doing the merge after we delete the 24. So we take the 19, 27, 29, and we end up putting them together. Okay, so we get 19, 27, and 29, but having done that, notice what happened to the traffic cop above. When we got rid of when we did the merge of the 19, 27, and 29, we didn't need 2 traffic cops up above. We only need 1 traffic cop up above. And that traffic cop just has to point to 30, it doesn't have to point to 27. So again, we only have 1 traffic cop up above. So we, in this case, we just have the 30, and we don't have to have a traffic cop for the 27 because it's only 1 node. You don't need to distinguish between 1 node in itself. You just go ahead and you have, only have 1 traffic cop. Unfortunately, that's not half full, so the parent got the problem from the kid. Okay, and can the 30 merge? No. The 30 can't merge. Let me go back to the previous page. The 30 ends up being a problem. It can't steal from its brother, because once we change the 2730 to just 30, it can't steal from its sibling over there, the 513, because that would reduce the 513 below 2. So you know what happens? We now only have a 30 at that next higher level. We now only have the 5 and 13 in the sibling. Well, guess what? D plus D minus 1 plus 1 is still less than or equal to 2D. You've got D things here, otherwise we could do the sibling theft. You've got D minus 1 things over there, because again, we went down below D when we got rid of the 27. And ordinarily, we'd be able to propagate up, but in this case, we can reduce the number of levels by 1 by taking the 2 things here, the 1 thing there, and the 1 thing there. D plus D minus 1 plus 1 is still less than or equal to 2D. So what ends up happening is we get rid of a level of the tree, and we're gonna have a root that ends up having the 5, 13, 17, and 27 in it. So, and 5, 13, 17, and 30, not 27. So this is a case in which, because we're not going to propagate to the root, because we're going to be able to do the thing where the root ends up getting combined, because there was only 1 thing in the root. The root already was, below par, and we can merge these things together. And notice that what happened is we ended up taking the 17, which had been the root, and we can pull it down. And these 4 things together become the new root. So the tree, which used to be 3 levels, is now only 2. And that's fine. So recursively, this all is going to end up working. If you end up having to hit the root, you may be able to pull the root down and be able to play with it. So we can pull the thing down, reduce the number of levels by 1. And this is a perfectly legitimate tree that reflects the result. Question about this? There's one question that somebody might have. That's on the next slide. I'm putting a value in, I'm taking a value out, I'm putting a value in, I'm taking a value out. Well, all these operations are log n. The insert was log n, because remember, I used log n to find something, and then I could propagate up at most log n levels to be able to do either theft from a brother or merging. In the worst case, I merge up log n levels. Same thing with the delete. With the delete, I search with log n, and then it might propagate up the whole tree. There are only log n levels in the tree. The amount of work I have to do to handle either the stealing from a sibling or merging is going to be, constant log n levels. So that's order log n, log to the base f of n, or basically log to the base D and then have full. But I could be in a situation where I keep merging and splitting and merging and splitting, and I'm getting dizzy. It's tiresome. It's still log in, it does get a little bit tiresome. What can end up happening, rather than thrashing and going ahead and doing this, is I might want to keep going, splitting and merging and splitting and merging. It's still log in, but I might want to prevent that. The thing that I can go ahead and do, well, I don't have any choice when something becomes too full and I can't fit 5 things into something that can hold 4. I have to split it. But I could go ahead and decide that the times that I want to do the merge are at a different percent. In other words, I'll do a percent when the 2 pages together, when 2 things together are say 80 or 90% full rather than 100% full. So, you know, I could do things on that where I avoid, you know, going back and forth. But even going back and forth, frankly, although it's kind of dizzying, is still log in. But I could avoid the thrashing back and forth by picking a different point instead of saying I only end up doing the merge only when it hits 100% full. I could choose to do the merge, let's say, when it's 80 or 90% full instead. It might be one way of dealing with that as a way of avoiding that. And now we're going to make a complete hash of it. Hashing is a wonderful algorithm, and we'll be seeing a hashing algorithm that you've probably never seen before as we talk about hashing as we go forward, which is, you know, a really, really nice approach to hashing, nicer than what you've seen in 101 for database purposes. And hashing is terrific for equality searches. Can hashing support range searches? Well, yes, sort of. If I'm searching for everybody whose age is between 20 and 25, I can look up 20, I can look up 21, I can look up 22, I can look up 23, I can look up 24, I can look up 25. So, you know, hashing kind of supports being able to do range searches. What if I'm searching for everybody whose salary is more than 1,000? Look up 1,000, look up 1,000 and a penny, look up 1,000, let's assume people aren't paid in fractions of cents. Look up 1,000 and 2 pennies, look up 1,000 and 3 pennies, dot, dot, dot. A lot of things are valued more than 1,000. Hashing is great for looking up exact values. If it's a very small range and the values, you know, don't have, you know, too you know, small granularity, it's not, you know, too hard to look for values. But for example, if I have, you know, intervals that are in microseconds and I'm trying to look for everything that's between 10 o'clock and 11 o'clock or something like that, I don't have to look for every single one. Hashing stinks for that kind of example. Now, I can always find, I mean, there is always a way that I can use hashing to find everything, or even find a range, which is a lot cleverer than trying everything down to the microsecond level. I can just search the entire hash table. I can always search everything in the hash table. After all, a hash table is a collection of buckets. I can just search all the buckets. So there is always a way to use the hash table to find things. But basically, hash index is a collection of these buckets. You've already learned about radix and hash and all sorts of other variations with buckets before. And basically, in the version, we're not going to deal in this case with you know, open addressing. We're going to say that basically the hash table is going to consist of a primary page, which can have a whole bunch of entries in it. You can have, you know, a whole bunch of entries in it. You can fill the page just as you could with the situation that we had with the B tree. You can have a whole bunch of entries in it, but sometimes things don't fit inside the page. You filled up the page and there's no longer any room. Everything is nice if everything fits in the primary page. You know, if you have a good hash function, maybe it'll work a lot of the time, but not all the time, because, you know, there could be a value that has a lot of records that correspond to it. A lot of people are located who go to UCSC or are located in the state of California. So you may have to have overflow pages that correspond to a particular hash value. Now, we're going to be looking at dynamic hashing later, but now we're just looking at static hashing. So the buckets contain the data entries. So you have a hash function, okay, in which you have the search key fields of the record. So it says H of R, but really what's going on is you take H of K. whatever the search key is, you're not gonna hash in the whole record, you're only gonna hash based on the search key. So really the slides should say H or K. So the bucket in which you put record R is based, you look at the search key inside R. So you're using state as being a lot of other things about a student, but you wanna find all the students who are from a given state. So even though the record has all this stuff about the student, you're only looking at the state to be able to do H of the state, not the whole record. So you look at the search key fields of R, not the whole thing, okay? And you know what? You can store everything inside your hash table. I mentioned that your index can store all the records in it. The hash table can store all the records in it too. Rather than using a heap or using a sorted file, you can store your records in your index, whether it's a B-tree index or a hash index. You can store all your records in it and have the records only there. So, having said that, now I'm finally going to tell you about data entries. I've already given you a feel for it. I'm going to give you a little bit more than a feel now, and I still have 9 minutes left. There are 3 alternatives, which again, because I'm boring, I will call alternatives 1, 2, and 3 for how K-star is stored. Remember K-star, K is a search key, K-star is the data entries that correspond to K. And the 3 alternatives are, I'm actually storing the data records in the index. And that's an alternative, whether it's a hash index or a B-tree index. I can store the data records inside the index. That works. Or what I can have as my data entries, and the next 2 are very, very close variations of each other. First one is very different. Alternatives 2 and 3 are close variations of the other. Alternative 2 says, what I'm going to do is, I'll store a key and an RID, a key and an RID, a key and an RID, so that every RID is there with its key. And the third alternative, which you might see has a slight difference from the second, is for each key, I'll store the RID list, giving me all the RIDs that correspond to the key K. So in the first one, suppose I have California. I have California and George, California and Martha, California and Lee, California and Chris, California and this, that, and the other thing. And I keep storing California every single time for every RID. And if there are 1,000 records that have California, I'll store California and the RIDs from 1,000 records. The difference in the second, that's alternative 2. Alternative 3, I store California and I have an RID list. Which one of these is better? Depends. The advantage to the first way is I have fixed size representation of things, assuming that the search key is fixed length. Everything has the form, California and an RID, California and an RID, Oregon and an RID, Oregon and an RID, etc. for each individual state. If I'm storing the key, in this case California, and the RID list, the size of the RID list will depend on how many RIDs correspond to that particular state. So which one is better? Think about programming it and which one you would like better. Remember, you have to program not only for the search, but also for insert and delete. Where again, you want to avoid wasting space and having too many pages. You only want to, split things when you have to, and all the rest of that at the leaf level. Okay, so we're just describing K-star, but 3 ways of doing it. Store the data in your index, in the leaf of the pages if it's a B-tree, in your hash bucket if it's a hash table. Second, store the entries in the form key and RID, key and RID, where the key value might have to be repeated multiple times. And remember, you know how to find records if you have an RID, which is a page ID and a slot ID. Isn't it wonderful how levels build on each other beautifully? Which means that if you're confused by the earlier stuff, you're meta confused by the later stuff. So it's good not to get confused by the earlier stuff.
Consistency is nice.
But the third approach is simply don't keep repeating the key, but you have to deal with the variable size of the severities that are associated. Okay? And basically, how do you store the data entries? It works whether you've got indexes. It works if you have, B-tree indexes, or if you have hash indexes or other things. You can use any of the three approaches to be able to deal with it. We've looked at B trees, we've looked at hash structures. I will say a little bit, possibly at the end as an optional lecture, about something called R trees, which are spatial ways of finding things spatially. I've decided, actually starting last year to focus more on LSM trees, which are more commonly used and more important than R trees, but there are lots of different things. What's the index job? To find the data entries. How are the data entries stored? You've got a choice. And so basically the RID alternative, basically 2 and 3, there are 2 alternatives that are based on RIDs. Alternative 1 stores the data. The RID alternative basically corresponds to the notion of there being indexes, which might be, and we'll go into this, might be primary key indexes or might be other indexes, which we call secondary indexes. And we will soon be talking about clustering indexes and non-clustering indexes. So let's just go through it. Alternative 1, the data records used in the index. In that case, the index is an organization for the data, not just for finding the data, but the data itself is there in the index. It not only finds the data is sitting there. It doesn't have a level of indirection. It's actually there. So it's an alternative to having a heap file or a sorted file. It's an index file with the data actually sitting right there. Unless you're willing to replicate your data, sometimes you are, but unless you're willing to replicate the data, you can pick this for only one search key. If you want to have the data multiple times, yeah, you could choose to have it for multiple things. You could have one on age and one on California and have the data stored based on age and based on state. That's a lot of data sometimes to replicate. You could choose to do it. It could be something that you regard as expensive. But normally in practice, usually if you're going to do this at all, you only do it once. Maybe you're not going to do this at all. So you typically will do this 0 times or 1 time. Again, not necessarily replicating. And that could be, an issue about having to have a lot of storage, a lot of memory, and again, having to deal with expensive updates. And of course, the disadvantage of this approach is that if the data records are reasonably big, the number of leaves that you have is really big, which basically says that, your fan out, at upper levels, the level above, it makes the index itself more expensive.
Question.
So, yeah.
So the leaf entries are it's a page, right?
The leaves are pages, and the pages have to hold data entries, and the data entries they hold may be the data records themselves.
And if the data records doesn't fit in one page, what happens?
In what we're assuming, we assumed in project 1 that at least one record can fit inside a page. And in practice, especially since pages these days are a lot bigger, you're typically going to be able to fit a number of records inside a page.
So we assume that it's always going to
project
fit.
1, always assume that you can fit a record in a page. Even with the overhead of the slot directory, always assume you can fit a record in a page. And in practice, again, because pages are big, you usually can end up fitting more records in. We're just playing with 4K, but in practice, it's a lot bigger these days.
Okay.
Almost done with the lecture in 2 minutes, and alternative 2 and alternative 3 are variations of each other. Data entries, if you're just having things with either the RID or the RID list, the data entries are much smaller than the records, so you can end up, going ahead and not having this, terrible large fan out at the level above the leaves. Alternative 3 is more compact than alternative 2, but because it is variable size, it's a little messier to deal with. So you have less space with alternative 3, because you only have to have the search key once, even if there are a lot of RIDs, but it's a little more of a nuisance to manage. Question?
So for the alternative 2, you store key record ID, and for the alternative 3, you store key and the list of record IDs.
Yeah.
There's the same number of record IDs in the alternative 2 as in the size of the list of the
Yeah, because
alternative 2?
if you have 500 students in California, you've got 500 students in California. The difference is how many times do you store California?
But will the sizing be the same?
No, because you only have to store California once, and one of them California many times than
This-
the other. And moreover, you know that you just have the RID. You have to have some way of representing the list if you're doing alternative 3. So alternative 2 has the advantage that it's fixed format, easier to manage. but it has the disadvantage that you have to deal with repeating the search key like California many different times, possibly in a compressed form. The other thing about having to store an RID list is you have to have some way of figuring out how many things are on the list and where the list ends and all the rest of that stuff. Okay. So that's what's going on. And now, we're not gonna get to this yet, but I will tell you what's coming. We'll be talking about different types of indexes, primary versus secondary. Thing on the primary key is a primary index, thing on something which isn't primary key is a secondary. And the really important thing that I'm not gonna try to go through now is the difference between clustering and unclustered or non-clustered index. What's a clustering index? The order of the data is the same as the order of the index. What's an unclustered index? It's not clustered. What the heck does that mean? We will explain in gory detail Monday. Have a great weekend.
You too, dude.